So, hello everybody, this is Dr. Ritu Singh from Basic Science Department, and today's the topic of discussion is corrosion. It is third lecture of unit 3. Now, corrosion, as we all know, it is degradation of the surface of metal, and corrosion is basically a process of oxidation. And oxidation occurs at anode. So, basically it is a process which is going to take place at anode. So, what is happening because of corrosion? Because of corrosion, the surface of the metal gets tarnished, and what is actually getting tarnished, or what is actually getting damaged is the useful properties of metals. The useful properties of metal, for example, malleability and ductility, which are only associated with metals. So, that is the effect of corrosion. So, corrosion, it is a process, a basic process is process of oxidation which occurs at anode, and here what is happening is the surface of the metal gets tarnished, degradation of the surface of metal. Now, the first question is, why do metals undergo corrosion? So, the metals undergo corrosion because we know that metals are present as mineral ores, and from mineral ores we extract pure metals. If we talk about mineral ores, they are very stable. So, because they are stable, they are present in ground state. Now, during the process of extraction of pure metal from mineral ores, a lot of heat treatments and other treatments are given to the mineral ore. So, this process of extraction of pure metal from the mineral ore is metallurgy, or we can write it as extraction process. Now, during this process, because lot of heat or other treatments or stress treatment are given to this mineral ore, then the pure metal which is present or which is extracted is not present in ground state, but it is present in excited state. So, anything cannot remain in excited state for a longer time. It has to come back to the ground state. To stabilize itself, the pure metal undergoes corrosion. So, this is why the metals undergo corrosion. So, although in the reaction we have written that it is a reverse process, but reverse process does not mean the pure metal is converted into mineral ore, because once the pure metal is formed, when something is happening or it tries to attain stability, it is going to cause some damage, and the damage is the surface of the metal is tarnished, or oxidation takes place at the surface of the metal. So, that is why corrosion takes place. So, corrosion is taking place, why? Because the metals they want to attain stability. Pure metal, after extraction, they are not present in ground state, they are present in excited state. And the effect of corrosion is this important properties of the metal get tarnished. Now, we have got different theories regarding the corrosion process, and the two important ones are, one is a dry corrosion, the other is a wet corrosion. So, dry corrosion. So, first we are going to take dry corrosion, and then we are going to take wet corrosion. So, these are two theories on which the corrosion is based as to how corrosion takes place. So, first we are going to take up dry corrosion. Now, dry corrosion can take place by three ways. One is oxidation by oxygen gas. The second is oxidation by any other gas other than oxygen, and third is liquid corrosion. So, again we are going to go one by one. First we consider oxidation by oxygen gas. Now, suppose this is a metal on which oxygen gas falls. Initially, a physical adsorption takes place, and then we increase the temperature. When we increase the temperature, the physical adsorption is converted into chemisorption, and as the chemisorption occurs, this metal undergoes oxidation. So when metal undergoes oxidation, we get ions. So I repeat, we are having a metal on which oxygen gas is adsorbed. This is done by physical adsorption. Then we increase the temperature. When we increase the temperature, the physical adsorption is converted into chemisorption and the metal undergoes oxidation. This is the reaction. The electrons which are released are taken up by oxygen and we have formation of oxide ions. Then these metal ions, they combine with oxide ions, forming a layer of metal oxide. So this is the whole process. Now this metal oxide layer which is formed can be a protective layer, it can be a stable layer, it can be a non-porous layer, it can be non-volatile. So if the layer which is formed is protective, stable, non-porous, non-volatile, insoluble, then, and there is one more term, insoluble, then the layer which is formed is going to reduce the rate of corrosion. If this metal oxide layer is non-protective, unstable, porous, volatile and soluble, then it is going to enhance the rate of corrosion. So depending upon the nature of this metal oxide layer, the further corrosion can be enhanced or it can be decreased. The rate of corrosion can be decreased. So this is oxidation by oxygen gas. We come to second one, which is oxidation by any other gas. Any other gas other than oxygen. It can be chlorine, it can be SO2, it can be carbon dioxide, it can be H2S. So these are just examples. Here corrosion depends upon the affinity between metal and these gases. Suppose I take up chlorine. If we are having a metal of silver, then chlorine has got an affinity for this metal, and because chlorine is having affinity for silver, so the layer which will be formed is a protective layer. Now the second condition, if I take tin in place of silver, if I take tin, then chlorine is not having affinity for tin, and because it is not having an affinity for tin, then the layer which is formed is a non-protective layer. So here the corrosion depends on what type of layer will be formed, whether the layer is protective or it is non-protective will depend upon whether the gas is having affinity for the metal or it is not having affinity for the metal. Then we have third, which is liquid corrosion. Liquid corrosion means, suppose this is a metal and I flow, this is a solid metal, on this I am going to flow a liquid metal. So we can have two things. What happens when as the liquid metal flows, it will wipe off the surface of the metal. And the second condition, that liquid which is flown can penetrate into this metal. So in both the cases it is going to cause corrosion. So this is third type, which is liquid corrosion under dry corrosion. Then the second is wet corrosion. It is also known as electrochemical corrosion. There is one more term which is used, is immersed corrosion. So what is here? Here we require an anode, we require a cathode and we require an electrolyte. So because electrolyte is used, so it is known as wet corrosion. Electrochemical, because we have an anode and a cathode, and whenever we are having anode, cathode and electrolyte, an electrochemical cell is set up. So it is also known as electrochemical corrosion. Immersed corrosion means anode and cathode, they will be immersed in a liquid electrolyte. So it is known as immersed corrosion. So if we talk about wet corrosion, here we have two reactions. One is anodic reaction and the other one is cathodic reaction. At anode we are going to have oxidation, as we have already done in electrochemistry, and cathode we will have reduction. So at anode we are having oxidation. Suppose we are having a metal, metal undergoes oxidation giving electrons. Now the electrons which are released at anode, they are taken up by cathode, and depending upon the environment of cathode, further reactions are going to take place. So we have got two anodic environment. One is evolution of hydrogen and second is absorption of oxygen. So these are the two environments which are present on cathode, and depending upon these two environments, further reactions are going to take place. Now evolution of hydrogen, when evolution of hydrogen is taking place, the medium is acidic, and acidic medium is, so hydrogen is present, oxygen is absent here. Absorption of oxygen takes place in neutral medium and oxygen is present here. So this is the difference. Now because the medium is acidic, so what will happen is the electrons which are released here, they are taken up by H plus ions and hydrogen gas is evolved. So this is the reaction which is going to take place at cathode. So if we take up the example of rusting of iron, at anode iron undergoes oxidation, 2 electrons, and at cathode 2H plus 2 electrons will give hydrogen gas. I have written the same reaction again. So the overall reaction is Fe plus 2H plus ions giving Fe plus 2 plus hydrogen gas is released. So this is rusting of iron in acidic medium. Iron is undergoing oxidation, and process of oxidation is corrosion. So this is evolution of hydrogen. Second, we consider absorption of oxygen where the medium is neutral. So medium is neutral means water is present. In the presence of oxygen will take up the 2 electrons or electrons which are released here, and there is formation of OH minus ion. So this is the cathodic reaction which is going to take place. Again the example is rusting of iron. So the reaction of anode at anode is going to remain same, which is Fe giving Fe plus 2 plus 2 electrons. These 2 electrons are taken up by cathode, and the same reaction or this reaction is going to take place, H2 plus half O2 plus 2 electrons giving 2 OH minus. Now in the third step, this Fe plus 2 ion moves to cathode and reacts with OH ions. FeOH whole twice. Ferrous is not stable, so it further undergoes oxidation because water is present and oxygen is present, and we get FeOH whole thrice. This is your rust. So this is rusting of iron in neutral medium. So if we see this one, the process of oxidation takes place at anode, but rust is not formed at anode, rust is formed at cathode. Why? Because if we compare Fe plus 2 ion and OH ions, Fe plus 2 ion is a smaller in size in comparison to OH ions. So it is easy for Fe plus 2 ions to move. So Fe plus 2 ion moves from anode to cathode, and then the whole process or the rusting or the rust is formed at cathode. So this is a wet corrosion. So here we are having two reactions, anodic and cathodic reactions. At anode we have oxidation, and when the electrons which are released, they move to cathode, and depending upon the environment of cathode we have two types of reactions. And this wet corrosion is very important. Now the next point is how anodic area is formed, or what leads to the formation of anodic area. The first is if impurity is present. Wherever on the metal impurity is present, that portion is going to behave as an anode. A rough surface, uneven surface, both of these surface, they are going to behave as anode. Third, the portion where oxygen supply is less, that portion is going to behave as anode. So these are the conditions where we can have the formation of anodic areas, or this is how anodic areas are formed. Next we come to types of corrosions. Under this, the first is galvanic corrosion. The galvanic corrosion is as we have done in galvanic cells. We have got two metals, one is going to behave as anode, the other is going to behave as cathode, and the metal which is having higher reduction potential is always reduced, and the metal which is having lower reduction potential will be oxidized. So with this, the metal which is having lower reduction potential will undergo oxidation, and the process of corrosion is the process of oxidation. So if we are having two metals, suppose A and B, this is having lower reduction potential and this is having higher reduction potential or electrode potential, then this metal will undergo oxidation. Oxidation of metal B is not going to take place. And secondly, if the electrode potentials of these two metals are different, then the rate of corrosion is high, and if the electrode potential or reduction potential of these two metals are close by, then the rate of corrosion is less. So this is galvanic corrosion, and galvanic corrosion depends upon the electrode potential or reduction potential of the metal. If the two metals are in contact, the metal which is having lower reduction potential will be oxidized. The second is concentration cells. Concentration cell corrosion. Now regarding concentration cell corrosion, we have got different examples of concentration cell corrosion. So in all the examples, we will keep up the metal taken as iron. So if we write the general reaction for rusting of iron in presence of oxygen and neutral medium, then at anode the reaction is iron undergoes oxidation giving Fe plus 2 electrons, and at cathode H2O plus half oxygen will plus 2 electrons will give 2 OH. Now at cathode what happens is these 2 electrons, they are taken up by water plus half oxygen and we get 2 OH minus ions. Now Fe plus 2 ions, they are going to combine with OH minus ions giving FeOH whole twice, which is ferrous hydroxide, which further undergoes oxidation because water is there, oxygen is there, and we get ferric hydroxide, which is rust. So in all the examples which we are going to take up, we are going to take up the example of iron, and this is the reaction which is going to take place. So at anode and at cathode. So in concentration cell corrosion, an electrochemical cell is set up. Why? Because we are going to see which area is going to act as anode and which area is acting as cathode. So anodic and cathodic areas, they are divided. Now the first type of concentration cell is differential oxygen concentration cell. So what happens here is we take a container. This container is filled up with an electrolyte. So when this is filled up with an electrolyte, I place a rod, and this rod is made up of iron, and inside this we are having any electrolyte. So the portion of iron which is dipped in this electrolyte, so this portion is going to act as anode, and the portion above the portion of iron above the electrolyte is going to function as cathode. The reaction at anode and cathode are same as I just now told you. Iron undergoes oxidation, the electrons released are taken up by cathode, and then there is formation of rust. So this is differential oxygen concentration cell. The portion of the rod which is present inside the electrolyte, the oxygen supply is less, and because the oxygen supply is less, so it is going to behave as anode. And once anodic and cathodic areas are separated, an electrochemical cell is set up and the metal undergoes corrosion. The second type of concentration cell is, the second is drop corrosion. Under drop corrosion is, we are having this metal, and here we place a drop of electrolyte. This is a drop of electrolyte. So what is happening here is, so this is metal. Now the portion of metal which is under this drop, this one, is going to act as anode, and the rest of the metal is going to act as cathode. So the reactions will be same, and as the cathodic and anodic areas are separated, the metal undergoes corrosion. So this is drop corrosion. The next we have waterline corrosion. Now waterline corrosion means we are having again a water tank which is filled up with an electrolyte, and again the tank is made up of iron. In the previous drop corrosion, the metal was of iron, because then the equation are going to remain same. So this is electrolyte, suppose NaCl, it is made up of iron tank. So the portion of iron which is under the electrolyte or till here, it is going to act as anode, and the portion above the electrolyte is going to act as cathode. And once the cathodic and anodic areas are separated, an electrochemical cell is set up. Then we have cervic corrosion. Cervix is an opening the places where metal is in contact with metal, or when metal is in contact with non-metal. For example, on the wood, if we do nailing, then metal is in contact with non-metal. So a cervix is created, an opening is created, and if this cervix comes in contact with moisture, then the water supply is cut off. And once the water supply, the supply of oxygen is cut off. And when the supply of oxygen cuts off, it starts behaving as anode, and the other part of the metal behaves as cathode. So once the cathodic and anodic areas are separated, an electrochemical cell is set up. So cervix, this is a cervix corrosion. Then the next concentration cell corrosion is pithing corrosion. The meaning of pithic corrosion is, suppose we are having this metal, and over this metal we are having a metal oxide layer. So this is metal, and this is the layer of metal oxide. What happens? By some means this layer develops cracks. So these are the cracks which are developed. When these cracks develop, this metal which is present beneath gets exposed. The portion where crack develops is going to act as anode, and the unbroken portion acts as cathode. Once the cathodic and anodic areas are separated, an electrochemical cell is set up. Then this is pithing corrosion. Next we have stress corrosion. Stress corrosion normally takes place in the metals which are fabricated, or the materials which undergo fabrication, or fabricated articles. Whenever the articles are fabricated or they are decorated, then they are passed to a large number of stress. It may be because of temperature or pressure. But after the fabrication is over, that stress is released. But sometimes what happens is, when the metal comes under stress, after the removal of stress, the metal still remains under stress. So the portion of the metal which is under stress will behave as an anode, and the portion of the metal which is not under stress is going to behave as a cathode, and thus an electrochemical cell is set up. So this is stress corrosion. So these are different type of concentration cell corrosions. The third type of corrosion which is important is exfoliation and selective leaching. Exfoliation, there are two different type of corrosions. Exfoliation normally occurs in aluminum alloys, and it occurs in the bulk. It occurs on a clean surface and then it moves upward. So it is a special type of corrosion. Selective leaching, meaning of selective leaching means we are having, suppose we are having an alloy of copper and zinc, and by some means I remove zinc from this alloy. So what will happen? This alloy will become porous. When it becomes porous, the mechanical properties of the alloy gets destroyed. So that is also a type of corrosion. So this is selective leaching. I am selecting one metal and then I am going to remove it. So these are different types of corrosions. Then we have factors affecting corrosion. The factors which affect corrosion are, they are of two types. First is nature of metal, and the second factors which are going to affect corrosion are from environment or environmental factors which affect corrosion. Now the first we consider the nature of metal. The first under this is electrode potential. So whenever we define factors, we are going to define as to when the corrosion is going to increase. So if we are having two metals in contact with each other and if their electrode potentials are far apart, then the rate of corrosion is going to increase. So this is electrode potential is going to affect. Second is anodic and cathodic area. Now, corrosion is a process of oxidation, and oxidation occurs at anode. But to increase or enhance the rate of corrosion, the anodic area should be smaller in comparison to the cathodic area. Why? Because cathode demands electrons. So, if the demand is going to increase, then the rate of oxidation is going to increase, and which will lead to the increase in corrosion. So for corrosion to take place or to enhance the rate of corrosion, then anodic area should be smaller and cathodic area should be larger. Third, impurity. If the metal is having impurity, then what happens is impurity introduces heterogeneity. At heterogeneity means there is a division of two surfaces. One is impure surface, the other is pure surface. The surface which is impure is going to act as anode, and the surface which is pure is going to act as cathode. And once the anodic and cathodic areas are separated, the metal undergoes corrosion. So this is impurity. D is grain size. Grain size, as in solid states we use unit cell. It is a repeating unit which when repeated again and again leads to the formation of whole crystal. Similarly, when we talk in terms of corrosion, we talk about grain size. So if the grain size is small, then it has more solubility, and when it has more solubility, then the rate of corrosion is faster. And then we have a specific volume ratio. The specific volume ratio is, suppose this is a metal, on this we are having a metal oxide layer. So specific volume ratio is ratio of metal oxide layer over metal. So for the rate of corrosion to enhance, this ratio should be small. So the metal oxide layer should be small if it is a protective layer. So this is a specific volume ratio. Then the next factor which will decide the rate of corrosion is solubility and volatility of the corrosion product. So I should rub it off. Solubility and volatility of corrosion product. So the corrosion product is this metal oxide layer. If the metal oxide layer is soluble and it is volatile, then it is going to enhance the rate of corrosion. So these are some of the factors which is based on the nature of metal, which are going to enhance the rate of corrosion. Now we come to environmental factors. Now the environmental factors are temperature, then we have pH, third is moisture, then we have acidic gases, fifth is suspended particles. So temperature. When we increase the temperature, the rate of diffusion increases, and when the rate of diffusion increases, the rate of corrosion is going to increase. Second is pH. Corrosion always takes place in acidic medium. So if the pH is less, the rate of corrosion is fast. Moisture. Moisture is a deciding factor in the rate of corrosion. Then acidic gases. If we see in the environment, we have got number of acidic gases like SO2 is there, CO2 is there, SO3 is there, and we have got traces of H2S. They all are acidic gases, and we know that in acidic medium the rate of corrosion is faster. So if in the environment, if we are having the presence of acidic gases, then the rate of corrosion is going to increase. The next is suspended particles. For example, ammonium chloride. If it is present in the environment, then it can react with the moisture which is present in environment and can function as an electrolyte. So once the presence of electrolyte is there, again the rate of corrosion is going to increase. Why? Because an electrochemical cell is set up. So these are the factors, environmental factors, which are going to affect the rate of corrosion. So the last topic is protection against corrosion. So under protection is we move stepwise. First we take up the nature of matter. Then we take up environmental factors. Now in nature of matters and environmental factors, both these factors we have discussed in factors affecting corrosion. But when we were discussing under factors affecting corrosion, we discussed them in a way where the rate of corrosion was increasing. But now here we are talking in terms of protection. So same factors we are going to discuss, but in the way that the rate of corrosion is decreasing. For example, if we talk about electrode potential, if the two metals, the electrode potential is nearby, then the rate of corrosion is going to decrease. If the metal is pure, then the rate of corrosion is going to decrease. If the specific volume ratio of the metal is high, the rate of corrosion is going to decrease. If the anodic area is larger in comparison to the cathodic area, the rate of corrosion is going to decrease. If the corrosion product, which is the metal oxide layer, if the metal oxide layer which is formed is insoluble and non-volatile, then the rate of corrosion is going to decrease. And the last, if the grain size is larger, then the rate of corrosion is going to decrease. So the same factors, when we are talking about the factors affecting corrosion, then we talk in terms where the rate of corrosion is increasing. Same factors we can take up in protection, but we are talking in terms where the rate of corrosion is going to decrease. When we come to environmental factors, here we just now talked about temperature. So if the rate of diffusion is less, if the temperature is decreased, rate of diffusion is left, the corrosion is going to decrease. To decrease the corrosion, the pH should be high, moisture should be minimum, or no moisture should be present. The presence of acidic gas should be less, or no acidic gas should be present in the environment. Environment should not have suspended particles. So if these conditions are fulfilled, the rate of corrosion will be decreased. So the first is nature of matter, second is environmental factor. Now if we cannot control these two things, then we go for actually the protection of metal, and under that the first is cathodic protection. Now under cathodic protection, the anode is forcefully converted into cathode, because the corrosion is a process of oxidation, and oxidation takes place at anode. So what we are doing in cathodic protection is we are forcefully converting anode into cathode so that the rate of corrosion can be decreased. Now the cathodic protections are of two types. First is sacrificial anode, and second is impressed current cathodic protection. So these are two types of cathodic protection, sacrificial anode and impressed current cathodic protection. So, these are two cathodic protections, sacrificial anode and impressed current cathodic protection. So, first I take up sacrificial anode. Suppose this is a metal, this is going to behave as anode and this behaves as cathode. So, what we do is we connect it to another metal whose electrode potential is less than metal to be protected. So, this part, the electrode potential of this metal is less than this. So, if we connect this metal to this system, what happens is this portion will not behave as anode. Now, this metal is going to behave as anode. So, this is sacrificial. Why? Because we are protecting this metal at the cost of this metal. So, this is sacrificial anodic or sacrificial cathodic protection. So, a anodic metal is connected to a more anodic metal. So, that more anodic metal undergoes corrosion. So, it is known as sacrificial because we are protecting one metal at the cost of another. The second type of cathodic protection was impressed current cathodic protection. Now, under this what happens, suppose this is a metal, this portion is going to behave as a anode and this is behaving as cathode. What we do is, we know that a cathode is an area where the electrons they come and from anode the electrons are going to flow. Now, to this area, by some means, if we start flowing electrons on this anode will behave as cathode. So, what we do is, this anode is connected to a DC source, and once it is connected to a DC source, the electrons they start flowing to this anode, and once the electrons starts flowing to the anode, this anode starts behaving as a cathode. So, this is impressed current cathodic protection. Next is anodic protection. So, if we cannot convert anode into cathode, then we go for second type of protection, which is cathodic protection. Under cathodic protection, what we do is we develop an metal oxide layer, and this layer is a protective layer. So, on an anode we develop a metal oxide protective layer which is going to decrease the rate of corrosion. So, this is anodic protection. Then we have third type of protection, which is protective coating. Now, in protective coating, what we are doing is we are breaking a contact between anode and cathode, or we say that we are isolating anode and cathode. Once anode and cathode they are isolated, then the rate of electrochemical cell is not set up. Then the protective coating is of two types. First is metallic coating, second is non-metallic. Under metallic coating, the first is electroplating. In electroplating, we coat a metal with a protective metal, and that protective metal is going to act as anode. The metal to be protected acts as cathode, and a salt of the metal coating metal is taken as an electrolyte. So, here the metal to be protected is taken as cathode. The metal whose coating has been done, that is going to behave as anode. And the example here is galvanization and tinning. Galvanization is applying a coating of zinc, and tinning means applying the coating of tin. So, this is electroplating. Second is metal cladding. What we do in metal cladding is we take up a metal. Suppose this is a metal which we want to protect against corrosion. So it is sandwiched between two coating metals. These are two coating metals, and the metal to be protected is sandwiched, and then the three are passed through a roller. What happens is this coating metal undergoes bonding. So when this metal bonds up with this metal, the metal in between, the metal which is sandwiched, is protected. That is metal cladding. The third is dipping. What we do here is the coating material or the coating metal is taken in liquid state, and suppose this is a metal which we have to protect, then this metal is dipped into that coating metal and taken out. So this is dipping. While dipping, the coating material gets over that metal. Fourth is spraying. Spraying means atomized droplets of the coating metal is sprayed on the metal to be protected. Suppose this metal I have to protect, then I am going to spray atomized droplets of the coating material so that it can be protected. So these are different types of metallic coating. Then we come to non-metallic coating. When we talk about non-metallic coating, they are of two types, organic and inorganic. Organic means we are going to apply paints, we apply varnishes, we apply lacquers on the metal surface. We apply varnishes on the metal surface, which not only protects the metal, but it is also going to decorate it. So this is organic coating. Inorganic coating means, for example, chromate coating or phosphate coating. This is example of inorganic coating. So what we do is we develop chromate coating or phosphate coating on the metal surface, and then just to protect it. Chromate is also going to protect and phosphate is also going to protect. So we develop a protective film on the surface, and the protective film can be of chromate or can be of phosphate. And another example of inorganic coating is misovit, which is applied on Ashoka pillar. That is also an example of non-metallic or inorganic coating. So these are protective coating. Now we have one more method for protecting corrosion, and that is corrosion inhibitors. Now corrosion inhibitors, they are substance which when added to the corrosion environment, it is going to inhibit corrosion or decrease the rate of corrosion. So they are corrosion inhibitors. They are of two types, anodic inhibitors and second is cathodic inhibitors. Anodic inhibitors means we are going to add amines, we add pyridine, or we add heterocyclic compounds. So when we are adding these substance, what is happening? A protective film is developed, and because of this the rate of corrosion will be decreased. Now this anodic inhibitor is also known as organic inhibitors because these are organic substance. So this is on anodic inhibitors when amine, pyridine or heterocyclic compounds are added to the corrosion environment, a protective metal oxide layer is formed. The second is cathodic inhibitors. Cathodic inhibitors, as we have just now done in wet corrosion, we have two types of cathodic environment. One is presence of oxygen, the other was absence of oxygen. And in absence of oxygen there was evolution of hydrogen. So first environment was evolution of hydrogen, and the second environment was absorption of oxygen. So what we do here is we add some substance like silicates or phosphates. If we add silicates and phosphate, what happens? The evolution of hydrogen is decreased, and when the evolution of hydrogen decreases, the rate of corrosion is going to decrease. Secondly, for absorption of oxygen, the second environment where oxygen is present, what we do here is we add a reducing agent. So when we add a reducing agent, what happens? The amount of oxygen is reduced, and once the amount of oxygen reduces, then the rate of corrosion is decreased. So that is corrosion inhibitors. So this is all in your corrosion.